Good morning. This is our turbine project. My name is Isabella.
I'm Nathan.
I'm Stacia.
Everyone worked collaboratively on the code via Zoom screen share. We interchangeably wrote the code, fixed bugs, and did pencil and paper sanity checks. For our code, we used the Redlich-Kwong equation of state, the Peng-Robinson equation of state, and also used an isentropic assumption to find exit temperature, ideal work, and then the turbine efficiency. The top part of our code is where we define our inlet and outlet conditions, as well as the constants for nitrogen. This will later be modified to fit the conditions for our technical reports turbine and the constants for steam. This part of our code used the Redlich-Kwong equation of state to calculate the volume and the actual turbine work, first using a constant heat capacity. Then we found work using a temperature-dependent heat capacity. We then implemented the Peng-Robinson equation of state and the temperature-dependent heat capacity to obtain actual turbine work. Then we calculated the entropy change between state 1 and state 2. Next, we analyzed the isentropic operation of the turbine to find ideal work. First, we found the new T2, knowing that the change in entropy must be 0. This gave us 230 Kelvin. Then, using this new T2, we calculated isentropic work. Finally, we calculated efficiency as the ratio of actual work over ideal work, and this answer was around 79.62%. Using the same code, but now modifying the constants and the inlet and outlet conditions to model our steam turbine from our technical report, we generated a 94% efficiency.
For our technical report, we chose an analysis of a steam turbine power plant within an existing phosphoric acid factory. This factory is located in Tunisia, and the report focuses solely on the steam turbine power plant within the factory as a whole. We're specifically going to be looking at a single turbine within that power plant system. This slide has a diagram of the full steam power system within the factory, and we're looking at turbine TB, which is within that red circle. For the inlet and outlet parameters, we took these from the report and used them within our code to model for efficiency calculations. And one thing to note is that our inlet parameters were given as a range in the report, and our group chose to focus on the lower end of the range and use the values 385 degrees C and 37 bar because they gave us the most accurate calculations.
And overall, our code gave us very reasonable values. For our nitrogen example in class, we got an outlet temperature of 230 Kelvin, which is what we were expecting. And we also got an efficiency of around 80%. And when we adjusted our code for the steam values rather than nitrogen, we got an outlet temperature of around 425 Kelvin. And it gave us an efficiency for the turbine of 94.8%, which is quite close to the 93% that the report said was its maximum energetic efficiency. Now, that is still a slight difference, and a few of the reasons that could have been could be the fact that we assumed that our turbine was both adiabatic and that there was negligible kinetic and potential energy changes, which in and of themselves for turbines are generally reasonable assumptions, but we don't know the physical organization of the plant, so we can't say for certain whether they are negligible. And we also took the report at face value whenever we used our low pressure and high pressure values and then an outlet. Likewise, we didn't account for the fact that the turbine was connected to a turbo blower, which had an inlet of dry air and water vapor mixture. And lastly, we didn't account for the fact that this facility doesn't use pure water, but rather seawater, and the salinity of the water could also have an effect on the efficiency and operation of the turbine. But overall, given our values, we think that our code worked quite well and we're happy with it. Thank you.